Electric current. So last time we were looking at static electricity. Static means not moving. In electric current, the electrons are moving. So we're going to define electric current as a flow of electrons. Electric current measures the amount of charge per second that passes a cross-section of wire. So our equation, we know from last time Q is the symbol for charge and T would be time. So our charge per time is our current. Current, we use the symbol capital I, and it's measured in the units of amperes. And an ampere is defined as coulombs per second because coulomb is the units for charge. So the current always flows from plus to minus, but something we should keep in the back of your head, because electrons are negative, the electrons are actually flowing from the minus terminal to the plus terminal. However, we don't ever use this fact in physics. We say the current flows from plus to minus. So let's say I got a battery and a light bulb here, and I hook it together in a circuit. That current is going to flow from the plus side of the battery to the minus side of the battery. In order to get a light bulb to light up, we need to have the current, the wire needs to be touching the side of the light bulb and the bottom of the light bulb. One of these terminals is soldered to the side and one of these terminals is soldered to the bottom. That way we have a complete path for the electrons to follow all the way through. So a problem they might ask you on the AP test is, what direction is the current going through this filament? Is it going to the right or to the left? The answer on this one would be going to the right, and we always have to explain those kind of answers because you're not allowed to guess and get free points on the AP test. You have to say it goes to the right because current flows from plus to minus. All right, so why does the current flow in the first place? We say that there is a potential difference that is causing the current. And the way I think of potential difference is the same thing of, why does a rock fall? We know when you lift the rock up, it has potential energy, mgh, where h is the height that you've lifted the rock up. This position, right where the rock is, has a potential whether the rock is there or not. If we take the rock away, we have GH at this location, and that GH is called the potential of that location. And as soon as I put an object there, then I have some energy, and we can get some motion to happen. The rock will be falling. So what if the rock fell through a thicker medium? Obviously, the rock's going to fall slower in the water than it does in the air because the water adds some resistance to it. In the air, we would call that resistance air resistance. In the water, we don't call it water resistance. It would be called drag or something like that. So the thicker the material that it falls through, the slower it's going to fall because a thicker material has more resistance. So the same thing is true with a current. If we're putting a current through a wire, there's different types of wires, and some of them have more resistance than the others, and as more resistance is going to make less current flow, so your light bulb will be less bright. All right, so back to our notes. Why does a current flow? Because there's a potential difference. Potential difference is a variable. We use capital V in physics. It is measured in units of volts, which is also capital V. And because of that, we sometimes make that mistake of calling this voltage when it's actually potential difference in physics. So we can think of the potential difference as the electrical pressure that causes the electrons to flow through the circuit. So the resistance is something that opposes or slows down the flow of electrons. And we use this term, we say it slows down the current. The actual speed isn't going slower, there's just fewer electrons flowing. But it's easier to think of that the current is slowing down. So resistance is measured in units called ohms. This is the Greek letter capital omega. We use that for the symbol for ohms. So this resistance depends on several things. One of them is the length of the wire. So this is the issue I have with the bands that I play in. I played in a salsa band for 15 years, and I played in a rock band for 33 years now. And one of the issues we have is when we're playing on a stage that's out away from electrical outlets, this one's out in the middle of a park, the people who hire us give us this big extension cord thinking we're going to run it all the way to the end of the park and plug it into a wall somewhere. Well, the longer this cord gets, the less and less power we can get through the cord, and we have all kinds of problems running our equipment. What the people don't realize is if you have a longer wire, it's going to increase the resistance. So to counteract that, we need to get a thicker wire. And they do make really long extension cords with really thick wires that are made for this kind of purpose. All right, so our resistance depends on the length of the wire and the diameter of the wire. It's actually the cross-sectional area. Other things that will affect your resistance are the material that the wire is made out of. We know that aluminum has a higher resistance than copper just because it's made of a different material. Another thing is temperature. Once the materials start to get hot, the resistance increases. And this is kind of a spiral effect because increasing the resistance makes it get even hotter, which makes the resistance even increase more. All right, so this is our equation. R is our resistance. Our length goes on the top, and that way if we double our length, we're going to double the amount of resistance. That's a problem my band has. If we double the area of the wire, however, we're going to cut the resistance in half. And I need to warn you, the wire is a circle, so the formula for the circle is pi r squared. So a trick question they'll give you on the AP test is saying, what if we double the diameter of the wire? Is what's going to happen to the resistance? If you double the diameter, that means your radius is doubled. And when you square that radius, we get a 4 in the denominator. So doubling your diameter will give you 1/4 of the resistance. All right, the last thing in the formula, this is the Greek letter rho, as in row your boat. And it is the symbol we use for the resistivity. The resistivity is the number that goes along with the different material. Each material has a different resistivity to it. So this is what a resistor actually looks like. Any kind of circuitry that we use in any of our electronics needs to have a very small amount of current, and so we need to put resistors in there to slow the current down so we don't melt the circuitry on our boards. Somebody who's going into electronics has to memorize the color scheme here. They measure the resistance using scientific notation. So the first digit in the scientific notation here is red. On our scale, red is a 2. The second digit is green, which is a 5, so we have 25. And then the third stripe tells the power of 10, which would be 3 here. So 25 times 10 to the third power is 2,500 ohms is the value of this resistor. And then the last color down on the bottom, it's either silver or gold, and it just tells how good the measurement is. Are you within 5% or within 10% of this measurement? All right, back to physics. So inside of a light bulb, this wire that they make the filament out of is made out of the metal tungsten, and tungsten has a very high resistance, and that means it's going to get hot very fast. And then when it gets hot, the resistance increases even more, and that causes it to get even hotter, and eventually it'll glow bright red. So this is what we use for the filament inside the light bulbs. To keep it from catching on fire and burning, they have to suck all the air out. And that's why the light bulbs are inside of a glass bulb. It has to be a complete vacuum in there, otherwise the wire will burn and melt. For things like a space heater or your oven, they have a metal called nichrome. And it's the same thing. It has a very high resistance to it, and it will get hot very quickly when you put electricity through it. Things with a low resistance, of course, copper, that's what most of our wiring is made out of. Silver has even lower resistance than copper, and gold has the lowest resistance of all the metals. For that reason, there's some circuit boards that these circuits, all these little connections on the circuit board are made out of gold and really good quality circuit boards. Most of the circuit boards, they have a copper alloy that they use for these ones. However, the little pins down on the bottom are all gold plated. if you're into high-quality stereo systems, Monster Wire has gold-plated terminals as well, just because gold has a very low resistance. All right, so these are all connected by Ohm's law. Ohm's law is just a formula. It says the potential difference equals the current times the resistance. And then potential difference is measured in volts, current is measured in amps, and resistance is measured in ohms. The other formula that goes along with this is the power formula. Remember, what is power? Power is the rate that energy is used. And in AP Physics 1, we use the equation power is energy over time or work over time. In electronics, we can calculate the power by multiplying the current times the voltage. So sometimes they'll give you a combination problem where they're asking about how much time does it take to use a certain amount of energy, and you have to calculate the power using I times V and then put it into this equation to figure out what the time is. Power is measured in the units of watts, which is a joule per second. Joule is energy and second is time. So that means when you're multiplying in ampere times a volt, it also comes out to a joule per second. Multiple resistors, when you're adding light bulbs or resistors end to end, you're adding more and more resistance, so our overall resistance, it just adds. Should be adding the resistance of the first bulb plus the resistance of the second bulb, or in this case, you're adding one resistor to another resistor. In our lab last week, we learned that there was another way to hook the light bulbs together that ended up lowering the resistance. This one, when you're putting them side by side, the resistances add by inverse. And so our total inverse would be 1 over the resistance of the first light bulb plus 1 over the resistance of the second light bulb. And that gives us 1 over our net resistance. End of notes.